I already did a first part on the chain rule, trying to show you folks how to break apart compositions of functions. Maybe that's a rusty skill. In this part 2 of the chain rule, I'm going to show you how to do, I guess, the chain rule the long way, showing you all the work. Part 3 I just made, and that is a little bit on why we need the chain rule. And in part 4, I'm going to show you the quick way to use the chain rule. I don't recommend jumping to part 4, the quick way, because then some of that stuff might not make sense. If you make it through this video, then the things that we're not writing in the quick way will make a ton more sense. And if you get stuck and you have a long chain of functions nestled one inside the other, I think you'll be able to attack that a little bit better if you've done this stuff the long way. So you should be able to break apart compositions of functions by now. If not, pause, figure out how to do that, refresh yourself. And we're going to use the chain rule to find derivatives of compositions of functions, and today it's the long way. So when I see cosine cubed x, I see this as y is equal to something cubed, and that is a u. U is a stand-in for a function. U substitution is a thing in lots of different places. That's just a little bit easier to see. And the something we're cubing is cosine of x. And so I'm in the habit, instead of saying u cubed, because it really doesn't matter what's cubed, if we took the derivative of x cubed with respect to x, that's 3x squared. If we take the derivative of t cubed with respect to t, that's 3t squared. If we take the derivative of y cubed with respect to y, that's dy squared. And so I'm not going to say the derivative of u cubed or whatever. I'm just going to say the derivative of something cubed is, well, 3 times that same something squared. And the derivative of cosine of x with respect to x is, well, and always will be, negative sine of x. So what about notation? Well, the notation, we don't want to write y prime or u prime. Let's write something that might help us a little bit more. Let's write dy du, the derivative of y with respect to u. And for the derivative of cosine with respect to x, we'll write du dx. We're expecting to get dy dx, that notation for the derivative of cosine cubed x. And so what we're going to do is we're going to say dy du multiplied by du dx is equal to, well, we'll write what dy du is equal to, 3u squared, and the derivative of, or du dx is negative sine of x. And so dy dx is just, I'm going to pull this negative out front from the sign, negative 3, instead of u squared, I'm going to go back and take, well, cosine squared, and they still have a sine of x. So we need the rate of change of this input function cosine, as well as the rate of change of the outer function that we're putting cosine into, the cubing function. Let's try that again. So hopefully you see this cosine of sine of x as a composition of functions. I see it as, well, y is equal to cosine of something, and that something is sine of x. So the derivative of cosine of something is negative sine of that same something. And our something is sine of x, which has the rate of change of cosine of x. You're going to hear me say the same words over and over. If you choose to do things using these words, it'll help, I believe, once we get to doing less work on the paper and more work sort of out loud. So we write, well, just the algebraic stuff, dy over du multiplied by du over dx, and make those replacements on the right-hand side. Dy over du is negative sine of u. Du over dx is cosine of x. And what are we going? We're going the other way. In terms of the rainbow, dy dx is equal to negative sine of, well, I don't want a u there, so I'll just leave a blank for a minute. And, well, what goes in there? Oh, what goes in there is this u equals sine of x. So this is sine of sine of x. Don't make the mistake and write sine squared. This is not sine times sine. That's sine as the input to another sine function. What about here? So the derivative of, let's rewrite this. So we have y is cosine of something, and that something is 4x squared. The derivative of cosine of something is negative sine of that same something. Our something is 4x squared. No. Our something is 4x squared, which has a rate of change of 8x. Let's go ahead and combine those. So dy du multiplied by du dx is dy du, negative sine of u, multiplied by du dx. And that doesn't look like a great derivative of cosine of 4x squared. We expect cosine of 4x squared to only have x's in it. So we'll replace the u inside of the sine with what u is equal to, 4x squared, and leave everything else the same. All right, let's break apart 2x minus 7 quantity cubed. So we have y is equal to something cubed. The something that's being cubed is 2x minus 7. The derivative of something cubed is 3 times that same something squared. Our something is 2x minus 7, which has a rate of change of 2. No, don't stop. So dy du multiplied by du dx is dy du multiplied by du dx. And what do we end up with? We end up with the derivative with respect to x of the quantity 2x minus 7 cubed is 3 times 2x minus 7 squared times 2. I'm going to stop there. That should be almost enough. You're welcome to practice on your own. But I do want to tell you why I'm choosing to use these words. So let's go back here and do this thing again. So in part 4, I'm going to go through the shorter way to go. And it'll make a ton of sense if you're practicing these words that, well, y is cosine of something, and that something is 4x squared. That's the wrong spot. The derivative of cosine of something is negative sine of that same something, and our something is 4x squared, which has a rate of change of 8x. Because when you're doing the chain rule, you'll actually need all of that. So let me show you what I'm going to do in the next video, or the part 4 video. So the derivative, and I'm just jumping to dy over dx, the derivative of cosine of something is negative sine of that same something. And that something is 4x squared, which has a rate of change of 8x. So we can jump to there, but that's a lot easier if you know the work you're not doing.